No,
Yeah,
no,
no,
there you go.
Hey! All right. Well, let's get started. Thank you. This is Megan Anderson. She comes to us today from Washington Geological Survey, which is part of the Department of Natural Resources. She's a physicist, seismologist originally, and she did her PhD in Arizona, I believe, in Tucson, at the University of Arizona, I believe that is. And she's worked in this field for a long time, and she works on lots of cool projects with the Washington Geological Survey. And I don't know if any of you ever go to their geological portal website, but they make awesome products and make them available to everyone, and it all looks really, really nice. And today, she's going to talk about her title, seismicity, seismicity specifically, I think. In the, so go for it.
Yeah. Okay.
Oh, yeah.
Oh, do you know how to do that?
Yeah. Oh, normally I do. Maybe it's under more. All right, loading.
Perfect.
Oh, and also let's do this too. You don't need to see yourself. Do we need to actually?
You put that down in the corner.
Can you do it?
Yeah.
You have a.
Yeah. There's just a logo in the corner of all these slides, so that's perfect. You know where I'm from. Okay.
Great.
Sweet. Okay. Thank you everybody for coming. I'm so excited to be here. I arrived at WGS 5 years ago almost. And I started going to different places and giving some talks, and people were getting to know me, and then COVID hit. So I never got to come to UW to give a talk ever. So I'm really excited to be here and show you what we're working on down at WGS. So I know this is the Seismo lunch talk, and I'm not going to be showing you a lot of seismic waves today because we're going to be talking about how to find faults that may be active and create earthquakes using other kinds of data. So I'm going to introduce the project that all of this research came out of, and then I'll talk about my talk. Okay, so, is this going to work now? That's what I'm doing. Enter? Nope. Yeah, if the mouse is on it. Oh, there we go. Okay, cool. So I'm not going to spend a lot of time on this slide. I think everybody in this room and online probably understands that tectonic setting out in Southwestern Washington. So our study area is the black box there on the upper left-hand side. And we all know that the modern strain field in Western Washington arises from a combination of plate motion parallel compression and then also north-south shortening due to a rotation of microplates within the North American plate that are well shown by GPS vectors, as you can see on the right. So we have those two forces at play. Our study area in Southwest Washington is shown in the lower left, and you can see the dark gray areas where we did our study. So it's quite a big swath of Southwestern Washington. A little bit about the geology there. The geology was mapped in the 1950s at 62,000 scale. And you can see the simplified geology off to the right. And the big fault in the area is called the Doty Fault. And it's tens of kilometers long from the 1950s mapping, west striking, north dipping, reverse fault. And in the 1950s mapping, it kind of stops at the southwestern corner of the Doty Hills. And so big faults that have a lot of displacement don't just stop. We know that. So something has to happen there. And we weren't sure what was the mapping wrong, or, is there something that we're missing? And so we wanted to go in and check the mapping. One of the things the Doty Fault does is it uplifts basement to the surface. And here we have crescent formation, just like we do in Puget Lowen. And the Doty Hills there, you can see off to the right, have basement at the surface. And so there's quite a lot of displacement on the Doty Fault, at least along a certain section of it. So one of the reasons that we chose this study area to work on is we got funding from the state to work on seismic hazards in Southwest Washington because of flooding along the Chehalis River. And so back when I was hired, the state was looking into maybe putting in a flood control structure on the Chehalis River. And they wanted to understand the earthquake hazards to do probabilistic seismic hazard assessments in that area. And so we were hired to do the geological work, and they decided not to put in the dam because the ecology studies indicated it would have a detrimental effect on the river. And so they decided not to do it. Yay, science works. But they wanted us to complete the geological study because if they do any sort of flood control project in the future, they'll want to know what the hazards are from these faults. So we actually completed the whole 3-year project and published our report. So you can see the goals on the right-hand side there. I'm going to talk only about 3 of them today. And the 3 that I'm going to talk about is we wanted to better constrain the length, geometry, and connections between the Doty fault and other faults in the area. We wanted to understand what other faults exist. If possible, we wanted to constrain the slip rate on these faults to understand how often they might create earthquakes. And we also wanted to establish the Doty fault's role in the regional crustal kinematics of the region to understand what kind of earthquakes it might create. And so those are the 3 I'm going to talk about during the first part of my talk. And kind of an aside that came out of this research is correlation between one of the aeromagnetic anomalies of the region and the seismicity. That's very interesting, and I particularly wanted to present to this audience. So this is the first time I'm presenting that, and so I'm really excited to show you. So I'm really going to kind of whip really fast through the first section, and I'm going to show you mainly results and not so much about methods. But we'll go through one set of methods that may be more unfamiliar to you, and then we'll spend some more time on this last one. Okay, so part 1. The Doty fault zone. So if you read the title, you'll understand what the results are. It's the centerpiece of a long-lived, slow-moving, transpressive fault system in Southwestern Washington. All right, we're done, right? No, you want to see why. Okay. I have a couple slides here about methods, which I'm not going to spend any time on. I think mainly I wanted to show you that we applied a whole array of techniques to understanding this fault system in Southwestern Washington. Everything from mapping the geology to different kinds of geophysics, geochemistry, a little paleomag. We threw the whole book at it. If you think that sounds like a lot of work, it is. And so we actually had 21 scientists work on this project over the course of 4 years. So it's a huge number of people. We had lots of young assistants working with us. We do hire young people who are just graduated. If you ever want to work on this kind of effort, keep your ears out. We hire people usually in April. And so we all had a part on making this happen. So I am the person who's the expert in potential fields, so applying gravity and magnetic data to mapping fault systems. And so I'm really going to focus on that for this talk, but there was a lot of geology mapping that went on and a whole lot of other geophysics that we worked on. And so there's a lot more to it than just what I'm showing you today. Okay, so what are potential fields, gravity and magnetics in particular, really good at in terms of finding faults? Well, they're really good at finding fault length, geometry, and the connections between faults. And the reason that we need it is shown by the upper 2 pictures in this slide. There are trees everywhere. There's vegetation everywhere, right? It's Western Washington. When you go and try to map the geology, you're not going to get great outcomes everywhere. And so the potential fields is like kind of connective tissue between the places that we can see the geology. To connect what we see in one place to another into an integrated story that goes across the landscape. And so we used aeromagnetic data from a 2016 survey flown by Rick Blakely, the USGS. He just published that on ScienceBase in 2020. And we also collected over 3,000 new gravity measurements across Southwestern Washington to make a brand new gravity map to use as well. Okay, so what does this do for us? So I'm just going to give one example slide. So if we have an area where we have high density and low density rocks, I'm using the gravity as an example here. The area where you have high density, you'll have higher gravity that you measure. An area where you have lower density rocks, you'll have lower gravity. And then if you have a very sharp, especially a near vertical boundary between the two, it shows up as a nice sharp gradient in the gravity map. And if you can find locations of those gradients, you might find places where you have faults. Or if you have like a steeply dipping contact, if your rocks have been lifted up on edge and are exposed to the surface, but covered by trees. And so the dense rocks are rocks like igneous, basalt or granite, and less dense are sedimentary. And on the right, you can see a quarry in our field area. We have basalts, we have sedimentary rocks, and so we have some really nice density contrast in the geology that help us use this technique really effectively. And magnetic data has very similar principles, and the igneous and the sedimentary rocks have really similar relationships, especially if you have basalt as your igneous rocks, which we do here. It's a little more complicated to interpret because the anomalies are more asymmetrical than the gravity anomalies, but we can use them in a very similar way. So we're going to just look at both. Okay, let's jump into the results. This is the aeromagnetic map of Southwestern Washington. And you can see the Doty Fault is labeled in the center. And one of the things that we can see is there's a nice, really linear transition between higher magnetization north of the Doty Fault and lower to the south. And that's showing off the uplifted crescent basalts up in the uplift to the north of the Doty Fault, as was mapped in the 50s. And then to the south, we have the Chehalis Basin, which is filled with sediments. And so we see the Doty Fault as a nice linear feature jutting across the surface. Shown with stars here are other features in the area that we took note of and said, hey, maybe there's our faults too, other places where we have a nice linear gradient in the anomaly map. And these could be a number of different things. The top of the basement rocks crescent formation is a nice marker that would, if you offset it, would show up in the map. We also have 2 units of the Columbia River basalts out here. Really far distal end of the Columbia River basalts actually flowed into this area. And so we have the top of the Sentinel Bluffs member and the Pomona member. And these are well dated. So these are also really good geologic and strain markers. So if we can figure out offset on one of those particular units, they're also nice markers in our geophysical maps, then we might be able to come up with rates. If we look at the gravity map, this is the new gravity map for the region. And again, you can see the Doty Fault is a nice linear feature, nice lineament here. And it actually continues, it's a little more broken up, but it continues further to the east. And so from the gravity and magnetic maps, we think that the Doty Fault actually doesn't just stop in Chehalis as the old map showed, but it actually extends a lot further to the east. The stars in this diagram also show other places where we see nice contrasts that are linear, and so they might be faults. And in contrast with the magnetic map, the top of the crescent formation is really the best marker here. The Columbia River basalts are generally too thin to show up in the gravity map, though across some of our transects, we have good enough data to be able to pick it out in a couple of instances. Okay, so I said I was going to talk mostly about results, so we're going to jump right into it. Oh, but first I have to give a nod to my geologist partners, right? I want to show you the area where we added new geological mapping. You can see that the USGS State Map program, we work a lot under that umbrella. And so those are the quadrangles in the center that have been mapped in the last few years under the State Map umbrella. And then we added 2 new areas of geological mapping under this project. And in particular, our mappers, Wes van Dassau and Tabor Reedy, spent a lot of time along this section of the Doty Hills that was mapped in the 50s, trying to check the geologic mapping and make sure it looked okay, and that the relationships were correctly interpreted, and add a lot more data to that to make sure everything was working really well. So we had really good geological constraints for our interpretations. Okay, now I think I'm jumping to results. Okay, so if you don't watch anything else in my talk, these are the 3 slides to look at. Are you guys ready? Are you sure? Yeah, all right, cool. So this is the fault map prior to our work. So we have the Doty Fault zone is there. It looks like it kind of stops at either end. We have a fault called the Copiah Fault, which is looking a little longer. And then the Willapa fault zone over to the left was mapped by Ray Wells. Actually, it was dissertation, I believe. And so those are kind of the three major faults that we were concerned about. Here's what it looks like after. Putting together all our geological observations and using the geophysics to connect areas where we have good geology. So the bold lines are where we have really good support from the gravity and magnetics and geology. And then the dotted lines are places where we have just mainly support from the geophysics, but it serves to connect areas where we understand things better. And so I'm going to pop up the fault names here. So we now have mapped out quite a few other major fault systems in this area. So you'll note that the Doty fault, I particularly mentioned at the beginning, the Doty fault comes and it actually does end here like they mapped in the 50s. They were right. They did really good mapping back then. But what happens is it connects to a fault that that we newly mapped that comes up through this zone, and we're calling this set of faults the Brooklyn fault zone. So that's a really important set of faults that was unknown before. The Willapa River fault zone comes and we extended it further to the north, and we think it connects over to a newly mapped fault zone called the North River fault zone. And in this area, we actually have a PhD student here, Kelsey Stanton, who works with Juliet, doing some work out there to understand that fault system a bit better. The Doty fault itself comes over and it goes through a series of steps and then comes and ends very close to the St. Helens seismic zone. So we're wondering if there was a connection between the St. Helens seismic zone and the Doty fault. And we think they do connect, but the nature of the connection is a little bit amorphous. We did a lot of work over in there, and it was very difficult to trace an actual fault that really connected into the fault zone. It looks like the faults just kind of dissolve into nothing over there. But there's probably some connection that we're just not understanding yet. In addition, we have some faults to the north. We have the Scammon Creek fault zone, which is quite long fault, and the Kapaya fault we extended and put in. This is actually a fault that was mapped in the 60s, the Rochester fault, but we put a lot more information on it, enough that we could put it on the map. So you can see that the fault network is really quite filled in, and all these faults, they don't just float around, unconnected to anything. They all connect to each other and form a network of faults that move through the area. Cool, so that's awesome. But we want to know more than just where do the faults go. We'd like to know more about their geometries, and specifically for probabilistic seismic hazard assessment, knowing the dip of the fault is really important for understanding the rupture and where shaking might focus. And so we can actually use the potential fields geophysics to help us understand geometry as well. And so to do this, we collected 12 high-resolution transects. You can see some of them here. We had 250-meter spacing on our data points across those. And I'm going to show you an example here from B to B prime. And this is a method that not a lot of people use, and so I want to explain it a bit more with an example from this line. In the panel here, we have the data. So in the top is the magnetic data. Those are points pulled from the Aeromagnetic map. In the middle, we have the gravity data. So those are points we measured on the ground. And then in the bottom, I'll have a panel where I show the cross. We're going to construct the cross section. And then what we do is put it through forward modeling software, and the one we're using is called GMSys, in order to make a supposition of what the subsurface looks like and then predict what the anomaly should be, right? So this is a forward modeling process, not inverse. To do this effectively, you have to have, it's really helpful to have subsurface constraint like well data, and we actually did have 3 on this line. So it's probably our best constrained line of all of them. We normally don't get this lucky, but it makes a great example. And then the surface geology is constrained by mapping. And so that's where this really great geologic mapping is really important to come in and provide us constraints. Otherwise, we could have almost any shape in the subsurface, but we need other constraints to really make it unique. And I worked with our mapper, Andrew Sadowski, on this cross section. So you're going to see his name pop up. Had a lot of back and forth with Andrew on this. So in this, I put in the wells and how deep they go. And then just underneath the subsurface, I've got the surface geology constraint from what he mapped. Okay, so how this works in practice, and I'm actually engaged in this right now with Andrew working over in Kittitas Valley on some new transects. So when I get back to WGS on Thursday, I'm going to be jumping right back into this process with him in different areas. So I start by playing around with different shapes in the subsurface. I only use magnetic and density properties for rocks that exist in the subsurface that we know are mapped in the area. We also collect samples and measure their densities and magnetic properties so that we have good constraint on those physical properties of the rocks. So I started playing around with different shapes and I try to answer questions like I show here, trying to see what kind of shapes at what depth actually fit these different anomalies. Then at the same time, Andrew's doing the same thing, except he's playing in kind of the structural geology space. So he's, really honing in on the surface geology and trying to understand what might fit the observations using structural principles and also stratigraphic relationships that he's constrained using the mapping in the area. So we have a bunch of that, and then we say, okay, let's show each other what we've come up with. So this was our first draft from both of us. The top is Andrew and mine is in the bottom. And you can see that there are differences, but there's also similarities. So for instance, we both have the crescent formation in pink here coming up underneath this broad uplift. So that's the Doty fault there. And then this is the Scammon Creek fault, this new fault that we didn't know how much offset was on that thing before we started. So really clear that there's an uplift, almost like plateau north of the Doty fault. And then both of those faults have strong reverse components. And that's shown in the relationships on both of these. Okay, cool. So I tell Andrew, I'm like, hey, but buddy, you need more offset on these faults. We can't match the gravity and magnetics by having just this tiny little bit of offset on the top of the crescent formation. And he says, yeah, but you're missing a whole formation, Megan. You didn't even put the Wilkes formation in there. That should be in your basin. And also, the sediments need to be more consistent thickness because of the sediment environment they're deposited. So we're putting in constraints from two kinds of geophysics and also the best geologic constraints we have all into the process. So then Andrew says, hey, Megan, I drafted this. It looks more like your model. Could this work? And I say, hey, let's try it, Andrew. So there it is. And you can see that line we've been trying to get the line that is in both panels is what's produced by the panel below to match the data that we had pulled from the profile. And so you can see we're getting pretty close. And so then we have a little back and forth and try to fit like the smaller scale things. And then in the end, we come up with this, which was in the publication. So we have a nice model of the subsurface and also the surface control. And we show, what's permissible for the geophysics, but then also detail added from the geology. So you can see that the cross-section from the geology is a little bit more stylized based on the geologic constraints, and the geophysics is a little bit more simple, but they agree very well in the end. So that's kind of how it goes. It's really true hypothesis testing and a lot of back and forth testing different hypotheses and trying to come closer and closer to a hypothesis that fits all of the data together. Okay, so here's some other cross sections of the Doty fault zone that we did in just the same way. There's one on the left that's to the west of the one I just showed you, and one on the east. And one of the things that we discovered is every single transect, the Doty fault has to be a very steeply dipping reverse fault, so dipping at 50 to 60 degrees. And so it's not a thrust fault, it's actually a reverse fault. And we have a good idea about the dip. In addition, we did transects across this Brooklyn fault zone to the west. And what we learned is that this one here is actually DD prime. And what we learned is that the faults over there are actually more shallowly dipping overall, dipping at only 35 degrees. In both fault zones, we have strong fault propagation folds that are in the hanging wall and footwall. And so there's folding that is bound up in the deformation along with the faulting. And many of these faults have kilometer scale dip slip displacement. So it's not just a tiny little offset, there's quite a lot of offset on these faults. So they're pretty consequential. Okay, what do I have next? Okay, so from these offsets, because we know the ages of some of the units here, we can start talking a little bit about rates. And we only do this if we are really confident in the results of the modeling process. In this case, we had really great results and everything was really well constrained, so we decided to give it a shot. So if we take the dip slip offset that we measure from our cross sections on the crescent formation, our dip slip long-term rate since the Eocene basically is on the Doty fault is 0.05 millimeters per year, and on the Fall River fault, which is in the Brooklyn fault zone, it's 0.09 millimeters per year. Yes, Joan. Mm-hmm. Mm-hmm.
How do you ensure that they're compatible with each other in 3 dimensions?
Exactly. And I'm going to get to that in just a second. Okay, yeah. In terms of the modeling process, I will say this is that we usually extend our models a little bit beyond the end of the cross section to make sure they're crossing each other. And so each time we construct a new model, if it's in an area where we already have one, we make sure they cross and that they're agreeing that they cross over. So that's one thing that we do in terms of like constraining geometries. But then we also want to consider how are these things acting as a whole. Like this is only dip slip offset, right? We don't know about strike slip, right? And so that's something we need to consider. So I'll get to that next. Great. So first of all, the shortening rates are going to be less than the dip slip rate. So the dip slip rate is a slip along the fault, and then the horizontal shortening is what's shown on the right there. So it's a little bit lower. These are quite low rates. And we also noted that it was very consistent that the east-west striking faults like the Doty fault zone has a lower shortening rate than the north-south striking faults like the Brooklyn fault zone. And this is kind of getting to what Joan was saying. So one of the things that we really honed in on and tried to understand is what happens to the Doty fault when it comes over to this corner here. And we really can see from the geophysics that most of the strain is transferred onto the Brooklyn fault zone. There's no faults hanging out over in here in the Grays Harbor Basin that can accommodate that strain. And so using that relationship, we said, well, actually, so if we have dip slip displacement on the Doty fault, let's say we reverse displacement on the Doty fault, that makes right lateral strike slip on the Brooklyn fault zone. And if we have thrust motion on the Brooklyn fault zone, that would result in less lateral motion on the Doty fault zone. So if we think about the relative rates between those two orientations, we can back out a vector of around north 60 east is basically the sigma 1 or the main strain axis in this area. And so I would say this is where the title comes from. All of these faults have some dip slip and some transpression and some strike slip on them. So it's a fully transpressive system. And I don't know, this fault geometry is just, I have never seen that before. I've talked to people who said, oh yeah, that happens in different places. You can have faults that come together at almost right angle and actually have displacement on both of them that's reversed, but that's the first time I've studied one like this. If we put together these rates, if we back out the rate that's along north 60 east, the shortening rate, it's a little higher than each fault alone. It's going to be 0.09 to 0.08 millimeters per year, but that's still really low. And as a comparison, I just want to point out that the Seattle fault is at least 0.9 millimeters per year. So we're an order of magnitude lower than something like the Seattle fault. So in terms of seismic hazard, we would say if this fault is still active, as it has been in the past, then the rate's really low and it probably doesn't make earthquakes as often. So I think this is a really successful story in terms of earthquake hazard, because we're instead of saying, oh, the earthquake hazard is high on this fault, we're actually saying it's actually a lot lower than other faults in the state. So that's really cool. Yeah, so conclusions from section 1. Oh, I'm doing good on time. Awesome. So we found the Doty fault. We figured out that it connects to the Brooklyn fault zone in the west And it looks like it connects to, or at least runs up to the St. Helens seismic zone in the east. And the Doty, with the Doty-Brooklyn link and other relationships between the different faults in the area, we infer an oblique north 60 east shortening vector. And it, over time, we also looked and compared, I didn't put it on here, but we compared the rates from different markers from both the top of the crescent, and then also we have those Columbia River basalts, which are much younger, and the rates before and after that are roughly the same. And so it's only 2 points, but at least it tells us that between those two timeframes, the rates are pretty consistent. Then, yeah, the long-term strike slip rate based on geologic time is 0.08 to 0.09 millimeters per year, so an order of magnitude less than faults that we know about to the north. And the part that I didn't talk about is we looked really hard for evidence of recent ruptures on these faults. It's very difficult in this part of the state because it wasn't glaciated. So we don't have this nice blanket of quaternary deposits to offset and make nice scarps and have nice dates on it. And we really struggled to find any evidence, and we didn't find any evidence of recent movement, but there are very few places to look down there. We did find offset of near surface units, but that didn't take us any more recently than, say, like the Miocene. So about the same age as the Columbia River basalts. So, but if it's moving at a really low rate, maybe there hasn't been offset in a long time, right? So it could be active, but very, very slowly. Okay, are you ready for part two? Yes.
So there's folding that happens.
Mm-hmm.
I'm really behind on the literature on if co-seismic folding happens, or if it's physically influenced.
Oh, that you might have co-seismic folding, maybe.
But so the vectors, the rates are lower if you have folding. Like
I think. Well, we determined the rates from the faults themselves, so it didn't include the faults.
Right, so folding would account for some of that, or not, or what was the?
I don't think we accounted for the folding because we just looked at the dip slip rates on the faults themselves. And so if there's folding back in the hanging wall, I don't think that was included in our estimate. So it might be a little bit more.
Right, and typically, is it lower or?
The folding rate? We didn't determine a separate one. That would be a great thing to do. Yeah. It might, well, but you know, if you had a little bit folding, there is some shortening that's bound up in that. Yeah, so there might be a bit, the rates might be a bit more if the folding is counted in with that, but probably not by much.
Right.
Might double it, but it won't increase it by tenfold, that's for sure. Cool. All right. So the second part is kind of a little bit of an aside to the original goals of the study, but I think it's really cool. And I'm thinking about it right now, and I really want to hear if you guys have ideas or are excited about it too. I really want to hear about it. So there's a huge aeromagnetic anomaly in Southwestern Washington. And during this study, we had to contend with it because it affected our modeling. And so I'm going to take you on the story about like how we learned about this thing, and then bring you back to seismicity at the end, where I show you an interesting relationship that I think is really important that we haven't fully thought through, but have some ideas about, and I would love more conversation if people are interested. Okay, so here's the initial problem. So you remember this cross section, that example that I show you. Notice in the magnetic anomaly, there's this regional north-south magnetic trend. And when we first started doing our modeling with the near surface geology, that trend was not due to anything that we could figure out geologically. So probably due to something deeper, really long wavelength, and in potential field geophysics, really long wavelength, it's probably coming from something more deeply seated. But the amplitude is 550 nanotesla, and that's a really high amplitude signal. You can see compared to this little bump that goes over, this is over the Lincoln Creek uplift with the Doty Fault to the south and the Scammon Creek Fault to the north. The amplitude of this trend is even higher than what we had from the near surface geology, which I think is pretty amazing. And I don't think I'd ever seen that before. So Our geophysical tech, Todd Lau, and I were scratching our heads going, what is going on here? What is happening? And so we ended up, I'll show you what we modeled to account for it that wasn't in my previous slides. So this is the same model on the right. You can see that the near surface units are grayed out so that you can focus on what's down below. Here's the crescent formation. And we had to put this big block of purple goo down in the crust. It's a very long wavelength means it's deep. And the high amplitude of the anomaly means it has to be a very high magnetization, higher than the crescent formation. The crescent formation has a magnetic susceptibility of 70, and don't worry if you don't understand that, I'm going to do some comparison. And by contrast, this block of material, which we're calling the South Puget magnetic crustal block, if anybody has a better name for this that's shorter, I'd love to hear about it. But it has a magnetization that is probably more than double the crescent formation where we modeled it, so 150. And when Todd and I were modeling this thing and saying, there's something down there that's making this crazy anomaly, we were looking up what could be that high. And the main thing that we found is peridotite. And so for the longest time, we were calling this the not peridotite body because we were like, how could there be this huge chunk of peridotite down in the crust? And so this is kind of the odyssey of trying to figure out what it is. So it could also not just be a block, it could actually have like zones in it grading to higher magnetism where we have it shallower. So we could actually play around with the geometry a little. We just made one block to kind of make it a little bit simple. So I realized there could be some other geometries that are possible. Okay, so our question at the end here is this for real? And how big is it? Like, what is this thing? How big is it? All we have is this trend on this cross section. So we stepped back and started looking at the aeromagnetic data for a bigger region of Southwestern Washington. I'm just going to like pause and say, hey, thanks Rick Blakely and colleagues for flying all these surveys over decades. He was really responsible with the USGS for getting all of this data flown. And again, that last survey was only released in 2020, flown in 2016. Really filled in the middle of the section of Southwestern Washington. So we weren't able to look at this data as a whole until very recently. So you'll notice in the compiled aeromagnetic map, all we see are the kind of these shorter wavelength features. We can see that, again, the Doty fault shows up nicely, all the stuff we were looking at before. And so you really don't see the long wavelength feature. So we really need to apply a filter in order to pull that away from the near surface features. So two options are something called upward continuation, so I'm not going to talk about, and a transformation called pseudogravity. And we chose pseudogravity because, I don't know, I think it works better to show off deeper anomalies, anomalies from deeper features. But both are Fourier transforms. You transform the data and apply the filter in the Fourier space. The pseudogravity is a weird name. It's better named magnetic potential. It's really technically what it is, but people call it pseudogravity. So now we're stuck calling it pseudogravity. It doesn't come from the gravity data. It comes from the magnetic data. This messed me up a lot when I was a young scientist. How it works, I'm not going to go through the derivation. You can read Rick Blakely's 1995 book if you want to see the whole thing. But kind of simply, because both gravity and magnetism vary as the inverse of R squared, we can derive Poisson's relation, which states that the magnetic potential is actually equal to scalar magnetization times the component of gravity in the direction of the magnetization divided by Newton's constant and density. So that's kind of a weird relationship. But you can combine it in Fourier space with the gravity to derive a relationship that basically equates turns the magnetic data into a gravity anomaly. It's crazy, but it works. And this is what it looks like after you apply the filter. So the resulting anomaly is proportional to 1 over the wave number. And so the transform tends to amplify low wave numbers, so long wavelengths from deeper sources. So this is a great filter to apply if you want to see kind of the longer wavelength anomalies from deeper features. Now, I've changed annotations here. My BB prime from before, that's now XX prime. So sorry about that, jumping to a different kind of talk here. So you'll notice that this kind of ramp, this trend in the magnetization is really on the southern edge of a very large anomaly that covers all the way through the Black Hills. Olympia is included, Northcraft over to Enumclaw, not Enumclaw, over to Yelm and that area over there, Eatonville. Very large magnetic high. And this is what we're calling the South Puget Magnetic Crustal Block. And this is what its position would look like. Notice in the south near the Columbia River down there, there's another high anomaly, and we're calling this the Catholimet anomaly. And yeah, Rick Blakey has been asking me what that is forever. And I keep telling him, I don't know, I don't have time to look at it. So we're looking at the other bigger one to the north, but maybe the same principles apply to both of those. Not sure. Okay, so we know where we have this high pseudogravity anomaly, but it'd also be nice to try to figure out, well, what's the area included within that. So you'll notice that in the cross section that we modeled, there's kind of a very distinctive edge to where we have the body coming up much more shallow into the crust. And so we wanted to try to identify this edge going all around the perimeter. So try to find the maximum gradient around the edge. So we took the first derivative of this data and found the maxima in it and traced it out. And the dark gray line is basically the boundary of the magnetically high area. You can see off to the right, there's also a light gray line. This is dividing an area where you have very high pseudogravity to the west and very low to the east. And we think that this is actually the edge of Seleucia in the crust. And I actually just wrote a paper about this to the north, and it's in review at Tectonics. So yeah, want to do a paper on this too. So might be able to say where Seleucia ends, which will be really fun. But we're really thinking about this pseudogravity anomaly in this presentation. So one of the areas that was a bit confusing, you'll see this area where it's blue labeled BHL. This is the Black Hills Low. And this is an area that has really strong negative magnetization instead of really strong positive magnetization in the pseudogravity data. And we know from paleomagnetic measurements of the surface rocks there within the crescent formation that a lot of them have strong reversed remnants. So they were developed in a time when the Earth's field was flipped from today. And so we think that that's actually still part of the anomaly. It was just developed during a time when we had a magnetic reversal. And it's an interesting L-shaped feature, which is interesting. Okay, so there it is, great. But what is it? What is it, right? And we were trying to figure this out. And this is, kind of where I'm kind of going out into the area where I'm still kind of thinking about these questions. Right. So we have a block of very high magnetism, higher than crescent, has this weird L-shaped segment with reverse remnant magnetization included. We're calling it not peridotite. It seems to have magnetization similar to peridotite, or is it peridotite? It would be nice to have gravity to go along with this to see if we also have a dense anomaly. Right? Unfortunately for our study, we used isostatic anomaly, which is we applied to the data a correction that removes long wavelength features from the data, so it's not appropriate for this kind of question. We really need to model or interpret complete Bouguer anomalies, and we're going to run some modeling with that going forward into the future. But luckily, someone actually already did that in the past, so I'm just going to show you that. This is a cross-section modeled by Carol Finn in the 90s, and it's a much longer segment. It goes from all the way to the ocean into the back arc. And you can see that she's got the coast, it's labeled coast range. Between the coast and the Cascade range, there's 2 blocks in there. And the lower crust, she says, is subduction complex or mantle. So peridotite. And the reason that she interpret it this way is the density she was getting for a big section of the crust there was from 2920 to 3080 kilograms per meter cubed. And that's really appropriate for peridotite. If we look at other types of rocks that could be a candidate for that kind of density, I have a list here of different rocks you might expect in the lower crust that have a similar density to that. And you'll notice that only peridotite and diabase have magnetizations that are closer to what we modeled in our investigation. So it's kind of looking like peridotite might be a good candidate for this, which is interesting, or not peridotite might be. So our current hypotheses, there's two, and again, we're just kind of starting to seek into interpretations. So any ideas about what you think this is, I'd love to hear. But we think it's a possibility it might actually be relic mantle accreted with silesia. And one idea we had is it might be a volcanic center. One of the things of note is that if we think about this as an entire block, it gets pretty shallow in some places. In the Black Hills, it gets up to 2 kilometers below the surface. So that's really shallow to have a really high density magnetization rock like peridotite. And I would think you'd only get that if you were close to a volcanic center. So that's kind of where that came from. Another idea we've been talking about with our geological colleagues is that after silesia was accreted, there was an Eocene extensional period. And another thought is maybe this area actually got intruded and invaded by volcanics during the Eocene right after silesia was accreted. But a lot of the geology suggests the locus for that volcanism is out over here, kind of to the south, not across the whole region. So not so sure about that one. I kind of like option A for now, but still kind of holding lightly to those hypotheses. Okay, cool. But what does it do today? What does this thing do today? So as we're analyzing our data on this project, I had printed out a picture of this kind of the early map that I pinned to my wall to kind of just look at it occasionally when I was zoning out and think about what it is and what it means. And I was working with Tabor Reedy on focal mechanisms in the area to we're trying to see if we had enough to do a stress inversion to understand the area near the St. Helens seismic zone and where the Jody fault come together, see if we can figure out what the stress is in that area. And so I was looking back at Tom Broker's 2017 paper where he relocated earthquakes in the Pacific Northwest and did a bunch of interpretations of them. And I was looking at my screen, I was looking at the wall and looking at my screen, and I noticed that there was a shape here that seemed to be repeated over here. There's an area in Southwest Washington where there's missing seismicity. And you know, when we started this project, we'd seen that there wasn't much seismicity in that area. From PNSN and other sources. So we actually put seismometers out during the project to just try to see if it was potentially that we just didn't sample it, right? And there isn't any. We didn't find any. There's like 3 earthquakes, I think, in 2 years or something. It was incredibly low. So I said, hey, we should look at what this looks like. So here's the pseudogravity anomaly with the seismicity on top. And this I think is really cool. So you can see the seismicity, it kind of comes up from the St. Helens seismic zone and it just kind of fans out. It's not like the area with the pseudogravity high has no seismicity, but it's just really damped down a lot. The Western Rainier seismic zone actually skirts the eastern edge, and then up in the north, that pod of seismicities along and just south of Tacoma Fault kind of stops when we hit the northern edge of the body. So from this, we're thinking it's either a strong section of the crust, or maybe it's dry, so higher effective stress leads to the fault's not actually slipping in microseismicity. One of the ideas I've talked about with Michael Bostock and his student Reed Merrill, they had an idea, so this is from his 2019 paper, that where episodic tremor and slip is located on the left-hand side of this diagram, and then on the right hand, it's the black boundary, is separated in space from the crustal seismicity location. And his interpretation in this paper was that where you have some sort of seal holding water in the slab, you have the ETS. And then once you get further, the slab goes further down, there's a place where that seal breaks and all the water can come out. And that's where it's coming through the crust and creating microseismicity in the crust. And so if we're thinking about maybe there's a relationship between this seismicity in the crust and the presence of water, our thought was, well, maybe this big block in the lower crust is actually blocking the intrusion of water into the crust. And so maybe we're actually just keeping it dry. So this peridotite or diabase block is consistent with either it being stronger, having a big block of crystallized rock is going to be stronger than laminated flows and pillow basalts of the crescent formation, or it could be blocking the fluid intrusion and keeping the microseismicity down. And that's similar to Reed Merrill's paper in 2020. He worked on a very similar idea underneath the Puget lowland, looking at Silesia and relocated seismicity. And so it kind of seems like it's maybe a similar thing here, potentially. But with either hypothesis, this block may influence mechanics of crustal deformation in Southwest Washington in a pretty consequential way. And so I think understanding more about it is really important. And I'm really excited to understand it from other data perspectives, such as with, traditional seismology. I think it'd be great to understand more about what the crust looks like down here. Okay, so conclusions for number 2. We have this block, it's a zone of anomalous magnetism and density. Right now, we're thinking it might be relic mantle from a large-scale volcanic center within Silesia. It's pretty devoid of microseismicity, and that could be due to a strong or dry crust or both. And if it's not deforming much, strain could be focused at the northern and southern edges, and so this might have an implication for seismic hazard going forward. Okay, cool. So if you want to read about this, there's a report. You can email me for it. It's an interim report published just for the Department of Ecology for the study that was funding all this work. And this summer, we're going to start to try to publish this as an internal publication. So it will be citable coming from WGS. And then we're probably going to pull out a couple papers to publish in journals as well to try to get it out to a more academic audience. And so that's the talk. So any other questions? I finished in time, even with the technical difficulties. Yeah, Renate.
I can confirm that bowling is real.
Yay!
Absolutely
Yeah. Yeah, because you've probably added more seismometers down there in recent years. Yeah. Yeah.
Yeah.
Mhm.
We have a low magnitude of effect.
Yeah. Yeah.
So if there's not been any effect,
We would have seen that. Yep.